Okay, so what we want to do today, we're going to look at something a little different. The last part of Unit 3, it's not hard stuff, it's really important stuff though. We're going to look at transformations of graphs. You might remember doing a little bit of this, maybe from Algebra 1, maybe even a little bit from Geometry 2. So the whole point of this is we're going to start with a very generic plane function called a parent graph, the easiest version of a certain type of function, right? So for example, if we're talking about a quadratic function, the easiest quadratic would be x squared. So our parent graph for all quadratic functions would just be f of x equals x squared. And then we're going to soup this up. It's like if you build your own sundae, right? You start with just vanilla ice cream, pretty boring. But then everybody in here, if we all went to the sundae place, everybody's going to come out with different creations because you're all going to have little different ideas on what to do at the toppings bar, right? So it's the same kind of thing here. We can start with the generic vanilla function, and we can turn it into any type of function that we want of that kind, right? It's got to be like a parabola or an absolute value function. Based on whatever the type of parent function you started with, we can make that have its own personality by doing some transformations, right? So we're going to focus on what those transformations are. Let's do that. So let's start off by just building a toolkit of parent graphs. Okay, so there's, we're going to look at probably more than we need right now, 6 or 7, something like that. Throughout the year, we'll gradually work with all of these, but for now, we'll probably only work with, maybe 3 or 4 of them in Unit 3, just so we get some different shaped graphs to work with. But that's really it. Okay, so let's start off with an absolute value graph. If the parent graph f of x equals the absolute value of x, very simple looking graph, it's a V. It's just a V. Notice that the vertex is at the origin, okay? And the right slope of the V, or the right leg of the V has a slope of 1, the left leg has a slope of -1. So this function, I want to point out a couple things here. This has in math what we call symmetry. Okay, symmetry in math is very important. It's a way to kind of legally cheat, take shortcuts. What symmetry allows us to do is to draw part of a function, and then without actually having to, among other things, it allows us to determine what the other part of the function is going to look like without having to do any work. In this case, by just reflecting. Right? Does everybody agree that if I were to, let's say on a piece of graph paper, if I were to draw the right leg, it's a piece of infinite graph paper, how about? If I were to draw the right leg of this absolute value function, which goes out forever, infinitely far, if I drew that with wet ink, and then I folded the paper, creased the infinite piece of paper over the y-axis and folded it over, the imprint of that ink would create the other half of the function for free, right? I wouldn't have to graph it. I could just reflect it over and leave an imprint, right? So that's what this symmetry does for us. So this is folding or reflective symmetry about the y-axis. That's where we make our crease in the page. Okay, we can do the same thing with our parent graph for x squared, right? The parent graph f of x equals x squared looks like a parabola. So instead of a V, now it's an infinite U, right? Vertex is still at the origin. And notice that I can still fold this thing over the y-axis to have it overlap. Okay, so it's got that same kind of symmetry. What about that one? What kind of symmetry does that one have? Yeah, what's going on there? Can I make a fold in the paper to draw the right half and create the left half? I can't fold it, but I could rotate, couldn't I? I could put a tack in the paper right there and just spin my infinite piece of paper half a turn, and then the right half would overlap with the left half, wouldn't it? Okay, so that's rotational symmetry about the origin. Okay. Notice in each of these examples that there was a kind of a special point, and we literally call it a special point in math, a special point that sort of anchors our picture. The vertex is the special point for an absolute value function. The vertex is the special point for a parabola. Notice that's where the fold is, right? It folds along through the vertex. That's the one point on the function that folds onto itself. Okay, so it's kind of a unique point. And then here, the special point is probably where? Okay, right there, right where you put the tack in the origin. Okay, what about this function? This is kind of a weird one. And this is, we're not going to talk, we won't use this one for a while. It's an inverse function. The inverse function has this kind of bizarre behavior, and this is interesting. The reason I bring this one up because it allows us to talk about something we discussed earlier. It's got asymptotes, right? It's got, would you agree that there is a horizontal asymptote for this function? It's the x-axis. In other words, if an ant were to walk infinitely far out to the right along this function, what would his y value approach? What do you think? If he walks, he's walking down this infinite hill, if he goes out infinitely far to the right, what y value do you think he's approaching as he goes out there? 1? It's hard to tell on this graph because it's just a snapshot, but the answer is 0. Yeah, it would just gradually get closer and closer and closer and closer to y equals 0, closer to the x-axis. It never gets there. Just like, remember this example, if I cut my distance to the door in half every second, I never actually get to the door, but I'm always approaching the door, right? Same thing up here. And then on the other side, if I had the ant walk backwards towards negative infinity, he'd be walking up this infinite hill, but it flattens out and flattens out. It never gets completely flat. His y value would once again approach 0, but never get there, right? So it's got a horizontal asymptote right here. And anybody see a vertical asymptote? Where do you think? Here. Right in the middle, right on the y-axis. There's a vertical asymptote. Right? Now that's a little different kind, essentially the same. The way this would work, if the ant were walking backwards along this function and he were approaching, trying to get to x equals 0, well, he'd never get there. As he walked back along this function, he would just continue to rise higher and higher and higher and higher as it gets steeper. And he'd kind of go up towards positive infinity in the y direction. And his x value would get closer and closer and closer to 0, but it would never get there, right? Opposite effect would be happening down here. If an ant were to walk along this function, the left half of this inverse function, towards x equals 0 from the left, he would plunge down towards negative infinity vertically, and he'd just get steeper and steeper and steeper. And every step he took, he'd get a little bit closer to the y-axis, but he'd just never get there, would he? Right, so we've also got a vertical asymptote. Okay, what kind of symmetry does this graph have? Rotational, doesn't it? I'm going to put the tack right there. All right. Okay. Is that weird? Is that point on the graph? I mean, it's on the xy plane, but the graph is just the part in red. Do you see that? So the ant could never step on that point. It's impossible. It's not on the function. It's not even on the function, but it is the special point because it's the only point it's the point that best describes this graph. It's the intersection of the two asymptotes, isn't it? And it's the point where we put the tack to rotate this thing. It's actually the most important point for graphing this function, even though it's not on the function. Okay, and then finally the last two, let's look at a square root graph. Square root graph has a starting point at the origin, and the ant can only walk to the right from there. Can't walk left. It's only defined for non-negative values. So you can't take a square root of a negative number and get a real result. So he can only walk to the right. He starts off with a pretty steep hill, but it just gradually gets shallower and shallower slope. And there is no asymptote for this one. If he walks infinitely far to the right, he'll walk up infinitely far also. But it only goes to the right. Is there any symmetry for that graph? No, you're right, there isn't it. And then related to that, very similar, is the cube root graph. Notice the cube root graph looks almost the same if you look at the right part of it. Okay? Only it's just a little bit steeper and sharper turn, but it looks very much like a square root graph. But the cube root graph does go to the left also, right? You can take cube roots of negative numbers. And so this one does have symmetry. What kind? Rotational symmetry. And where's the special point? At the origin. Yeah. It's not as glamorous, but where is the special point for this function? The origin, it's the starting point, right? The starting point is the important point for this one. It actually does have an end point there, okay? Okay, so let's try a couple things. Let's see what happens here if we want to do some easy transformations. Well, we're going to talk about translations today. Translations are just shifts or slides. You slide the function, horizontally or vertically kind of thing. Or maybe we'll even do a combination. Okay. In terms of the parent function f of x, what do you think happens if we do an outside translation? So that means we're going to add a number outside of the function. Goes up or down? Yeah, let's try that. Let's see what happens. We'll give that a try. So here's a graph of y equals x squared, right? There's our parent graph. The red graph is actually y equals x squared plus k, but right now the value of k is set at 0. So if I drag this little slider down here, it's going to change the number that we're adding to x squared. If I make that a positive number, not surprisingly, look what happens. The graph gets picked up. It's translated vertically. If I add a negative number, which is the same as subtracting, then it's moving in the positive direction, for example, by negative 1.8. Well, how do you move up negative 1.8? You go down 1.8, right? So if you subtract a number from a function or add a negative number, it translates it vertically down. Okay? No big deal. So we can see an example of that here. If we take the parent graph, f of x equals x squared, and we can make a t-table out of that. Here's my input column. These are the values of x, and these are the outputs when I square the input. So 2 squared is 4, 6 squared is 36, etc. Right? And if we graph this thing, we get the red graph. That's our parent graph. Those are all the points that correspond to these ordered pairs on our table. All right? Well, what happens if we add 25 to the function? We're just adding 25 to all of the outputs, aren't we? Right? That serves to just pick the whole thing up. I don't know what that's. So if we pick this whole thing up by 25, that's what it does, right? It just moves it up vertically by 25. Okay, makes sense? Okay. How about something different now? Let's try. I got a new challenge for you. We're going to try to do a different kind of translation here. So, where did I put that? There, no. Yeah, this guy. Okay, so look what we started with here. We've got f of x equals x squared, and I want to do something like, I want to feed that function a number that's going to make it, I want to think of a way that I can maybe make this thing slide to the right. That's my goal. We know how to translate vertically. Now we want to see if we can learn how to translate horizontally. Okay? Remember how you think about a function now. A function is just an input-output machine. That's all it is. You feed it inputs and it spits out outputs. The function doesn't care where the input numbers come from. It's just got a rule that it follows, and it's going to do whatever it's told to the inputs to give you the outputs. But what if our rule is just squaring? If our rule is we're just going to square something, right? That's its only job, is to square stuff. That's easy to do. If I feed the thing a 4, it's going to output a what? 16. If I feed it a 10, it's going to output 100. Okay, so my goal then is, if I want to slide this thing to the right, I've got to trick this function machine somehow. I know that, for example, when we'll draw on this. Give me 1 second here. There we go. So I know, for example, that when x is 0, 0 squared is 0, right? When x is 1, x is, once again, when x is 0, 0 squared is 0. When x is 1, 1 squared is 1. When x is 2, 2 squared is 4. If I want to slide this thing to the right, somehow I've got to trick the function, right? If I want to slide it to the right by, let's say, by 4. Okay? If I want to slide it to the right by 4, when I'm actually inputting a 4, I need the function to think that it's squaring. So I want this point right here to slide over to the right. 1, 2, oops, 3, 4. I need it to slide over to the right. So that's the point we're looking at, isn't it? Yeah. So instead of seeing a 6, I need it to think that it's seeing a 2. See the trick?
Yeah.
The coordinates at this point are 2, 4. I want the coordinates instead to be 6, 4, right? I want to take this whole thing and just slide it, the whole piece of it, every infinite, all the infinite points on this function, and slide them all to the right. So I got to go 4 to the right. I need when I'm inputting a 2, excuse me, when I'm inputting a 6, I'm saying this wrong, when I'm inputting a 6, I need the function to spit out a 4 instead of 36, right? Because I want to get that point. I want to input a 6 and output a 4. How can I do that? The number that I'm squaring needs to be what? To get a 4, what's the number I'm squaring need to be? 2. Okay, so then I've got to do something to my input. My input is a 2. I've got to, you fill in the blanks here. Fill in the mystery blanks. Actually, I'm inputting a 6. I'm inputting a 6. And you fill in the blanks because I need the function to think that it's getting a 2. Minus 4. Right? That's really all I'm doing from the input is I'm just subtracting 4, aren't I? Do you see that? If I subtracted 4 from the x value that I'm feeding the function, then instead of a 6, it's actually going to end up squaring a 2. So it's going to give me back a 4, 2 squared. Right? Do you see that? So let's try that. Let's just see if that works. So if we did that right then, if our thinking is correct on this, you're telling me that if I were to, for example, if I want to scoot this thing to the right by 3, I should do what to x? Subtract 3 inside the function, right? Because inside the function is everything that the function's being fed. Let's try that. So if I let the value of h, which we're going to call h the value that's being subtracted from x, if I let that equal 3, sure enough, look what it does. It slides it to the right by 3. Okay, how do you suppose I would slide something to the left then? Okay, I could subtract a negative value, which is the same thing as adding, isn't it? So if I want to slide it to the left by 3, I would have x minus negative 3, which is x plus 3 inside the parentheses. Okay, good. All right, so then this maybe summarizes what we just said, doesn't it? Can't do that. So if I start off with f of x equals x squared, and I want to do something, I guess I called it h here instead of g. Pretend it's g. G of x equals f of x plus 4. Well, think what that's doing then. That should slide it left or right. If I'm adding 4 inside the function, I should slide it left. Okay, it does, right? We start off with our basic parent graph with the vertex at the origin, and this produces a translated graph that's been slid to the right by, or left by 4. Okay? Do you see why that is now? Here's another way to look at it. If I'm creating this new function, which is f of x plus 4, well then take an example like right here. If x equals 4, that's a bad one. Let's take x equals 1. If x equals 1, x squared is 1. Well then if x is 1, what's x plus 4? 5. So that's moving us clear down to this row, isn't it? Right? So when we input a 1, because we're adding 4 inside the function, I'm actually squaring 5, which gives me back a 25, right? So when I go over to x equals 4, instead of getting back 0, I'm getting back 25. Notice the scale is way out of whack here, right? It was clear up. Does that make sense? And so it does slide it to the left. What's being done to that one? If we're starting off with the parent graph, now be careful with this one. If our parent graph is f of x, somebody tell me, first of all, what is that doing? It's going down, isn't it? How come it's not going left or right, it's going down? Because it's outside. It's an outside translation, right? We're adding a -5 outside the graph, and so this is telling us we're going down 9.5. Okay, now be careful with this one. What about this part right here? Okay, it's going left by 1.5. How come it's not right? Because it's a positive, right? Because the value, the amount that the function is being shifted to the right is what we call h, and that's the number that's being subtracted from x. That's confusing, right? It's confusing. So when it's inside the function, the direction that the thing gets slid is always kind of the opposite of whatever's happening to that number. If it's being subtracted, it's actually going right instead of left. It's backwards, right? Okay. So you're right in saying that this is going to go left 1.5. Okay. How would I do that? Let me think about this one for a second. If my parent graph is f of x equals x to the 4th, how could I do these two things? How could I go, first of all, let's move our parent graph down 7. So we're going to call this new graph g of x. So f of x is x to the 4th. How do I go down 7? Subtract 7 outside. Good, so we'll go -7. Now, how do I do left by 13? Okay, I'm going to add 13 inside the parentheses, so I'm adding it directly to the x. Well, I don't see any parentheses there yet, but I'm going to need some, aren't I? So where would the parentheses go? Okay, yeah, so it's inside the graph. Well, what's this graph doing? It's a power function, right? It's taking whatever, it's taking something to the 4th power. So then, there's where the parentheses are, right? Inside the function is the stuff that's being taken to the 4th power. And so what's going to go there? X. The quantity x plus 13 to the 4th minus 7 would do what we wanted it to, right? Do you see that? Okay, there's an assignment. Oh. There's 19 questions on the assignment. Seems like a lot, but they go pretty fast. See if you can get through half of it by the end of the period. I bet you can get close.